There are roughly 200 billion galaxies in the observable universe, possibly more. Each one holds hundreds of billions of stars. Around those stars orbit trillions upon trillions of planets, many of them sitting in the temperate zone where liquid water can pool on the surface. The raw ingredients for life, carbon, hydrogen, oxygen, nitrogen, are among the most common elements in the cosmos. Chemistry is not rare. Energy is not rare. Time is not rare. The universe has had nearly 14 billion years to run the experiment. And yet, when we aim our most sensitive instruments at the sky, when we listen across every frequency we can imagine, we hear nothing. No signals, no megastructures, no evidence that anyone, anywhere, has ever built anything. The silence is not just strange, it is statistically violent. It is a data point so extreme that it demands an explanation. And the most disturbing explanation that fits the math is this. Somewhere between dead matter and a starfaring. Civilization. There is a wall. A barrier so lethal that almost nothing gets past it. Physicists call it the Great Filter. And we do not know which side of it we are on. Let us begin with a number. There are roughly 200 billion stars in the Milky Way galaxy alone, possibly as many as 400 billion. Not in the entire universe, just in our galaxy. Our single spiral arm neighborhood in a cosmos that contains, by current estimates, somewhere around 200 billion galaxies, with some models suggesting the number could be significantly higher. Each of those stars is a furnace, burning hydrogen into helium, flooding the surrounding space with energy. And around those furnaces, planets are forming. Not occasionally. Not as a rare fluke. The Kepler Space Telescope, launched in 2009, revealed something that changed the way astronomers think about the cosmos. Planets are not the exception. They are the rule. Nearly every star you see in the night sky has at least one planet orbiting it. Many have several. The current estimate is that the Milky Way contains somewhere between 100 billion and 400 billion planets. Of those, a meaningful fraction sit in what we call the habitable zone, the orbital distance where temperatures allow liquid water to exist on the surface. That fraction is not tiny. Depending on the model, it could be as high as 1 in 5 for sun-like stars. That gives us billions of potentially habitable worlds in our galaxy alone. Now, layer in the chemistry. The 4 most common chemically reactive elements in the universe are hydrogen, oxygen, carbon, and nitrogen. These are not exotic. They are not rare. They are everywhere. And they happen to be the 4 elements that make up roughly 96% of the human body. The amino acids that form the backbone of life on Earth have been found in meteorites, in interstellar dust clouds, in the tails of comets. The raw materials for biology are scattered across the cosmos like seeds on a field, and the field has been sitting in sunlight for nearly 14 billion years. So you have billions of potential worlds, you have the chemistry arriving for free, you have energy pouring in from every direction, and you have a timescale so vast that it humbles the human imagination. The Milky Way galaxy is roughly 13 billion years old. Earth itself formed about 4.5 billion years ago. That means our galaxy was already 8.5 billion years old before our planet even existed. There were stars being born and dying before the sun's raw materials had even condensed out of their parent nebula. If life can emerge from chemistry, and if intelligence can emerge from life, then other civilizations had a multi-billion year head start on us. Some of them could have arisen when the galaxy was young. They could have been building technologies, launching probes, and colonizing neighboring star systems, while the atoms that would eventually become Earth were still scattered across a molecular cloud. This is not speculation. This is arithmetic. And the arithmetic leads to a prediction. Even if the odds of life arising on any given habitable planet are small, even if you make the probability 1 in a million, the sheer number of candidates means the galaxy should be teeming with civilizations. And even if the vast majority of those civilizations are primitive, Even if only 1 in a million reaches the technological stage where they can manipulate energy on a planetary scale, the numbers still work. You should still end up with thousands of detectable civilizations in the Milky Way alone. And here is where it gets worse. Once a single civilization develops the ability to travel between stars, even at a fraction of the speed of light, the math says it could colonize the entire galaxy in a remarkably short time. Estimates vary, but most models place the full colonization window somewhere between 1 million and 100 million years. In cosmic terms, that is nothing. The galaxy is 13 billion years old. Even 100 million years is less than 1% of its total lifespan. If even one civilization in the history of the Milky Way had started expanding at any point in the last several billion years, their presence should be everywhere by now. Their energy signatures should be unmistakable. Their structures should be visible. Their signals should be deafening. And yet, when we listen, we hear nothing. This is the Fermi paradox. It is named after the physicist Enrico Fermi, who, during a casual lunch conversation at Los Alamos National Laboratory in 1950, reportedly looked up from his meal and asked a question that has haunted science ever since. Where is everybody? The question sounds simple, almost childlike, but the weight behind it is enormous because Fermi was not asking out of idle curiosity. He was pointing at a gap between what our best models predict and what we actually observe. The prediction says the galaxy should be noisy, crowded, and full of evidence of intelligent activity. The observation says the galaxy is silent. And in science, when the prediction and the observation disagree, it means something is wrong with the model. Something fundamental is missing from our understanding. Either our assumptions about the likelihood of life are catastrophically wrong, or something is actively preventing civilizations from becoming visible. Something is stopping them, slowing them, or destroying them before they can leave their mark on the galaxy. For decades, scientists proposed dozens of solutions to the Fermi paradox. Maybe civilizations are hiding. Maybe they're too far away. Maybe they are using communication methods we cannot detect. Maybe they simply do not want to talk to us. These explanations are interesting, and some are plausible, but most of them share a common weakness. They require a specific behavior to be universal. They require every civilization, everywhere, across billions of years and billions of stars, to independently make the same choice. All of them hiding. All of them going silent. All of them choosing not to expand. That is a very strong assumption. It is a bet that every poker player at every table in every casino on Earth will fold at the same time. It only takes one exception to break the pattern. It only takes one civilization that decides to build, to broadcast, to expand. And across a galaxy with hundreds of billions of planets and billions of years of opportunity, the odds of zero exceptions are vanishingly small. This is the logical pressure that gave rise to the concept of the Great Filter. It was formally proposed by the economist and futurist Robin Hanson in a paper published in 1998. Hanson was not interested in telling a dramatic story about aliens. He was interested in solving a probability problem. He looked at the gap between the expected number of visible civilizations and the observed number, which is 0, and he asked a precise question. What kind of statistical barrier would be required to produce this result? His answer was the Great Filter, and its definition is deceptively simple. The Great Filter is the idea that somewhere along the path from dead matter to a galaxy-colonizing civilization, there exists at least one step where the probability of transition is extraordinarily low. So low that across all the planets in the observable universe, across all the billions of years of cosmic time, almost nothing makes it through. The filter is not a single event. It is not an asteroid or a plague or a nuclear war, though any of those might be symptoms of it. The filter is a statistical choke point. It is a point in the developmental sequence where the odds drop so close to 0 that, for all practical purposes, the transition almost never happens. To understand this, you have to think about the full journey that matter has to take to get from a dead rock to a starship. It is not one step. It is a sequence of steps, each of which has its own probability. Hansen laid them out roughly as follows. First, there must be a habitable star system with the right kind of planet, in the right orbital zone, with the right chemistry available. Second, on that planet, simple self-replicating molecules must arise from non-living chemistry. This is abiogenesis, the origin of life. Third, those simple replicators must develop into something like prokaryotic cells, simple single-celled organisms without a nucleus. Fourth, those simple cells must give rise to complex cells with internal structures, what biologists call eukaryotes. Fifth, those complex cells must organize into multicellular organisms with specialized tissues. Sixth, those organisms must develop brains capable of complex behavior and eventually intelligence. Seventh, that intelligence must produce a technological civilization capable of manipulating its environment on a global scale. Eighth, that civilization must survive long enough and develop the capability to expand beyond its home planet. Ninth, it must actually expand and become visible on galactic scales. Each of these steps is a gate. Each gate has a probability of being passed. If you multiply all the probabilities together, you get the overall probability that a given habitable planet produces a visible civilization. And the Great Filter hypothesis says that at least one of these gates has a probability so close to zero that it dominates the entire equation. It does not matter if all the other steps are easy. If one step is nearly impossible, then almost nothing gets through the full sequence. The filter acts like a bottleneck in a pipe. You can widen every other section of the pipe as much as you want. If one section is a pinhole, the flow rate is determined by the pinhole. Now, there is something important to understand about the way this argument works. The Great Filter is not a theory about what specifically kills civilizations. It is a theory about the mathematical structure of the problem. It says that the silence we observe requires an explanation, and the simplest explanation that fits the data is that one or more steps in the sequence are functionally impossible. The specific identity of the filter, which step it is, remains an open question. And as we will see, the answer to that question has radically different implications for the future of our species, depending on where the filter sits. Let us look at this from a purely mathematical angle, because the numbers are what make the Great Filter so disturbing. Consider the Drake equation, a framework proposed by astronomer Frank Drake in 1961, to estimate the number of detectable civilizations in the galaxy. The equation multiplies together a series of factors: the rate of star formation, the fraction of stars with planets, the fraction of planets that can support life, the fraction where life actually arises, the fraction where intelligent life develops, the fraction that develop detectable technology, and the average lifespan of such civilizations. The equation itself is not controversial. It is just a way of organizing the question. The controversy is in the numbers you plug in. For decades, optimists plugged in generous numbers and concluded that the galaxy should host thousands or millions of civilizations. They pointed to the abundance of planets, the commonality of the right chemistry, and the long timescales available. They assumed that if conditions were right, life would find a way. But the Great Filter reframes this optimism as a problem. If the optimistic estimates are correct, then the expected number of visible civilizations is enormous, and the observed number is zero. That gap is not a mystery to be explained away with clever hypotheses about aliens choosing to hide. It is a mathematical crisis. It means that somewhere in the Drake equation, at least one of the factors is not just small, it is catastrophically, almost unfathomably small. Small enough to cancel out the enormous number of opportunities the galaxy provides. Hansen framed this using a concept from probability theory. Imagine you are rolling a die with 1 trillion faces. You need to land on face number 1 to pass through the filter. You get 1 roll per planet per billion years. Even with trillions of planets rolling for billions of years, you might never hit that number. That is the kind of improbability we're talking about. Not 1 in 100, not 1 in a million. Something closer to 1 in a number so large that writing it out would fill pages. The silence of the galaxy is screaming at us that somewhere in the chain, the odds are astronomically stacked against success. And here is the thought that should keep you awake at night. We do not know which step is the filter. We do not know if we have already passed it or if we are walking toward it right now. This uncertainty is not a gap in our knowledge. It is the central problem of the entire framework, because the implications of the filter's location are not just scientifically different, they are existentially different. They determine whether our species has a future measured in billions of years or a future measured in centuries. Consider the 2 possibilities in their starkest form. Possibility 1, the great filter is behind us. This means that one of the early steps, maybe abiogenesis, maybe the leap to eukaryotic complexity, maybe the development of nervous systems, was the bottleneck. We already passed through the pinhole. We are the winners of a cosmic lottery so improbable that we may be the only ones who have ever won it. In this scenario, the silence of the galaxy is explained by the fact that the early steps are nearly impossible. Life simply does not start on most planets, or it starts but never becomes complex. We are rare. We are precious. And the road ahead, while challenging, is not blocked by any fundamental barrier. The stars are empty, not because civilizations die, but because civilizations almost never get started. Possibility 2. The great filter is ahead of us. This means that the early steps, abiogenesis, multicellularity, intelligence, were relatively easy. Life starts frequently. Complexity arises on many worlds. Intelligence is not a miracle, but a predictable outcome of evolution given enough time. In this scenario, the galaxy has been producing civilizations on schedule for billions of years, but none of them are visible. None of them made it to the colonization stage. Something wiped them out. Something reliably, consistently, universally destroys civilizations after they reach a certain level of technological development and before they can spread beyond their home world. If the filter is ahead, then we are not special. We are not rare. We are simply the latest in a long line of intelligent species marching toward a cliff that we cannot yet see. And the silence of the cosmos is not the sound of emptiness. It is the sound of a graveyard. This is why the Great Filter is not merely an academic curiosity. It is, in a very real sense, the most important question our species can ask. It sits at the intersection of astrobiology, physics, philosophy, and existential risk. It connects the search for extraterrestrial intelligence directly to the question of whether humanity has a long-term future. Every piece of data we gather about the prevalence of life in the cosmos is, simultaneously, a piece of data about our own survival odds. Every barren world we find is a quiet vote in favor of our rarity and our safety. Every microbe we discover on another world is a quiet vote in favor of the filter being ahead of us, waiting in the dark. The formal structure of the Great Filter is what gives it its power. It is not a story. It is not a metaphor. It is a logical constraint derived from observation. We observe silence. We know the galaxy is old, enough and large enough to have produced visible civilizations, if the full sequence were reasonably probable. Therefore, the full sequence is not reasonably probable. Something in the chain is broken. The filter exists, whether we like it or not. The only question is where it sits and how hard it is to pass. Some people hear this argument and object. They say that maybe we are simply not looking hard enough. Maybe civilizations are using technologies we do not understand. Maybe they operate on timescales or energy scales that make them invisible to our current instruments. These are fair objections, and they are taken seriously in the scientific community. But they face the same problem as the hiding hypothesis. They require universality. They require that every single civilization in the history of the galaxy has independently adopted the same undetectable mode of existence. No exceptions. Not one species in billions of years, on trillions of planets, that decided to build a Dyson. Probability of clearing all gates is near probability of clearing all gates is near zero. This makes it a more robust explanation than any hypothesis that depends on uniform behavior among species that have never met each other. There is one more thing to understand before we move forward. The Great Filter is not a single wall. It could be a combination of barriers distributed across multiple steps. Perhaps abiogenesis is hard, and the leap to eukaryotes is also hard, and self-destruction is also common. In this case, no single step is the entire filter, but the compound probability of clearing all the difficult steps is still astronomically low. This distributed filter model is, in some ways, the most troubling of all, because it means there is no single enemy to identify and defeat. There is no one wall to climb over. Instead, the path to the stars is lined with a series of progressively narrower gates, each one shaving off a fraction of the survivors until almost nothing remains at the end. This is the framework we will be working with for the rest of this journey. The Great Filter is a statistical argument about the rarity of the full transition from chemistry to cosmos. It is motivated by the observed silence of the universe, a silence so profound that it constitutes one of the strongest data points in all of science. It tells us that the journey we are on, the journey from organic molecules in a warm pond to a species capable of asking why the sky is quiet, is either a miracle that has already happened or a tragedy that is still unfolding. The next question we must ask is, which steps are the most likely candidates for the filter? Where along this immense developmental chain does the probability crash? To answer that, we need to look backward. We need to examine the deep history of life on Earth and ask ourselves a disquieting question. Was our path here easy, or was it a sequence of near impossible accidents that just happened to break our way? Because if the history of life on Earth is a series of flukes, then maybe we have already stumbled through the filter without knowing it. And if the history of life on Earth looks smooth and inevitable, then maybe the hardest part is still coming. Either way, the silence is watching. And the silence has an opinion. To figure out where the Great Filter sits, we have to do something counterintuitive. We have to stop looking at the sky and start looking at the ground. Specifically, we have to look at the history of life on our own planet. Earth is the only data point we have. It is a sample size of one, which is terrible for statistics, but invaluable for understanding what the sequence of transitions actually looks like from the inside. Because if we can identify which steps in the development of life were genuinely hard, which ones took suspiciously long, which ones appear to have happened only once in 4 billion years, then we can start to build a map of where the filter might be hiding. And if we are extraordinarily lucky, we might discover that the hardest steps are already behind us. Let us start at the very beginning. Not the beginning of the universe, the beginning of life. The transition from non-living chemistry to the first self-replicating molecular system. This step is called abiogenesis, and it is arguably the deepest mystery in all of biology. We know that it happened. We are here, which proves it. But we have never observed it happen a second time, not in nature and not in a laboratory. Despite decades of effort, no team of scientists has ever taken a flask of simple chemicals, applied energy, and watched a self-replicating system emerge from scratch. We have come close. We have produced amino acids. We have assembled short chains of nucleotides. We have created lipid membranes that spontaneously form bubble-like structures resembling primitive cells. But the full leap from chemistry to biology, from molecules that react to molecules that copy themselves with enough fidelity to undergo natural selection, that leap remains unreplicated. This is striking, and it cuts in two directions. On one hand, the fact that we cannot reproduce abiogenesis in a controlled laboratory might mean that we simply have not found the right conditions yet. The early Earth was a vast and chaotic place, with hydrothermal vents, volcanic pools, tidal zones, and atmospheric chemistry that we can only partially reconstruct. Perhaps abiogenesis requires a very specific combination of environment, chemistry, and time that we have not yet stumbled upon in our experiments. On the other hand, the fact that we cannot reproduce it might mean that it is genuinely, staggeringly improbable. It might mean that the leap from chemistry to life requires a sequence of molecular accidents so unlikely that even with a planet-sized laboratory running for hundreds of millions of years, you would be lucky to see it happen once. The geological record gives us a clue, but it is an ambiguous one. The Earth formed approximately 4.5 billion years ago. For the first several hundred million years, the surface was a hellscape of molten rock and constant bombardment by asteroids and comets. This period is called the Late Heavy Bombardment, and it effectively sterilized the planet. Any chemistry that might have been inching toward life was repeatedly destroyed. The bombardment began to taper off around 3.8 to 4 billion years ago, and the earliest evidence we have for life on Earth dates to roughly 3.7 to 3.8 billion years ago. Some researchers have argued for even earlier dates, pushing toward 4.1 billion years based on carbon isotope signatures in ancient zircon crystals. But even using the conservative estimate, the implication is remarkable. Life appeared on Earth almost immediately after conditions became even marginally tolerable. The window between the end of the bombardment and the first signs of biological activity is geologically tiny, perhaps a few hundred million years at most. At first glance, this seems like evidence that abiogenesis is easy. If life sprang up this quickly on Earth, then maybe it springs up quickly everywhere. Maybe any rocky planet with liquid water and the right chemistry will produce life within a few hundred million years. If that is true, then abiogenesis is not the filter. The galaxy should be crawling with microbial life, and the bottleneck must lie elsewhere. But there is a counter-argument, and it is a subtle one. It involves a concept called observation selection bias. We can only examine planets where life did arise, because we are the life that arose. We cannot survey the billions of planets where chemistry churned for billions of years and never produced a single self-replicating molecule. Those planets are invisible to us. They have no biologists to study them. The fact that life appeared quickly on Earth might not mean that abiogenesis is easy. It might mean that we are looking at the one lottery ticket out of trillions that happened to be a winner. If you only interview lottery winners, every single one of them will tell you that buying a ticket worked out great. That does not mean buying a lottery ticket is a good investment. This observation selection effect means that the speed of abiogenesis on Earth tells us very little about its probability in general. We cannot distinguish between a universe where life starts easily on most habitable worlds and a universe where life starts only once in a trillion attempts, but we happen to be sitting on the planet where it worked. This uncertainty is maddening, but it is also precisely where the great filter framework becomes powerful. It tells us that if abiogenesis is the filter, then the galaxy is full of beautiful, habitable, and completely sterile worlds. Oceans of liquid water with no one swimming in them. Atmospheres rich in the precursors of biology with no one breathing them. The chemistry arrives, the energy arrives, and nothing happens. For billions of years, nothing happens. The molecules bump and react and fall apart, and never once do they stumble into the configuration that crosses the line from reaction to replication. If that is the reality, then we are essentially alone at the microbial level. There is no one out there, not because civilizations destroy themselves, but because the first step was so improbable that it almost never occurs. But let us assume, for the sake of the argument, that abiogenesis is not the filter. Let us assume that simple life arises readily on habitable worlds. What happens next? The history of life on Earth gives us an answer, and it is not a comforting one. Because after simple life appeared, almost nothing happened for an extraordinarily long time. The first organisms on Earth were prokaryotes. These are the simplest possible cells. They have no nucleus. They have no complex internal structures. They are, in essence, tiny bags of chemistry. Bacteria and archaea are modern prokaryotes, and their basic design has not changed dramatically in billions of years. They are spectacularly successful at what they do. They colonize every conceivable environment on Earth, from boiling hot springs to frozen Antarctic lakes, to the crushing pressures of the deep ocean floor. But they are simple. They do not form complex bodies. They do not develop tissues or organs. They do not build brains. A planet covered in prokaryotic life is a planet covered in slime. It is alive, but it is not going anywhere. On Earth, prokaryotic life dominated for roughly 2 billion years. 2 billion years of bacteria. To put that in perspective, the entire history of complex animal life on Earth spans only about 600 million years. The age of dinosaurs lasted roughly 165 million years. The entire history of the genus Homo is roughly 2 to 3 million years. Modern civilization is a few thousand years old, and prokaryotes ran the planet, unchallenged and unchanged in any fundamental way, for 2 billion years. That is not a short pause. That is a wall. What broke the wall was the single most important event in the history of complex life, and it appears to have happened exactly once, somewhere around 2 billion years ago, give or take a few 100 million years depending on which evidence you prioritize. A prokaryotic cell engulfed another prokaryotic cell, and, instead of digesting it, began to live with it. The engulfed cell did not die. It continued to function. It continued to produce energy. Over time, it became integrated into the host cell, losing its independence but gaining protection. This event is called endosymbiosis, and the engulfed cell eventually became what we now know as the mitochondrion, the organelle that powers virtually every complex cell on Earth. This merger was the birth of the eukaryotic cell. Eukaryotes are fundamentally different from prokaryotes. They are larger. They have internal compartments. They have a nucleus that houses their DNA. They have an energy supply, the mitochondria, that allows them to sustain a level of metabolic complexity that prokaryotes cannot match. And critically, the energy surplus provided by mitochondria is what allowed eukaryotic cells to maintain much larger genomes. Larger genomes mean more genes. More genes mean more proteins. More proteins mean more structural and functional complexity. Without mitochondria, you do not get complex cells. Without complex cells, you do not get animals, plants, fungi, or anything else that is visible to the naked eye. Every multicellular organism on Earth, every tree, every insect, every fish, every human is a descendant of that one original merger event. And this is where the filter candidate emerges with startling clarity. Endosymbiosis of the type that produced mitochondria appears to have happened only once in the entire history of life on Earth. Once, in 4 billion years, on a planet saturated with prokaryotic life. Bacteria were everywhere. They were interacting constantly. They were engulfing each other, competing, cooperating, exchanging genetic material. And yet, in all that time, the specific merger that produced the eukaryotic cell occurred a single time. Every eukaryote on Earth, from yeast to oak trees to blue whales, traces back to that one event. Biologist Nick Lane has argued extensively that this is not a coincidence. He proposes that the merger between an archaeal host cell and a bacterial endosymbiont was not just rare, but structurally improbable. The problem is not the engulfing itself. Prokaryotes engulf other prokaryotes all the time. The problem is the survival of the engulfed cell and its stable integration into the host over evolutionary time. This requires a delicate balance of gene transfer, metabolic cooperation, and reproductive synchronization that is extremely unlikely to arise by chance. Lane calls it a bottleneck so narrow that it might explain the entire 2 billion year gap between the origin of life and the origin of complex cells. If he is correct, then endosymbiosis is a plausible candidate for the Great Filter, or at least a major component of it. Think about what that means for the galaxy. If abiogenesis is easy, but the jump to complex cells is almost impossible, then the universe might be teeming with microbial life. Mars might have bacteria, Europa might have bacteria, Enceladus might have bacteria. Every warm, wet world in the galaxy might be covered in a thin film of simple organisms. But none of them will ever become anything more. They will sit in their prokaryotic prison for billions of years, cycling through the same simple metabolisms, never developing the energy infrastructure needed to support complexity. A galaxy full of life, but a galaxy completely devoid of minds. Let us continue up the chain. Suppose that eukaryotic complexity is also not the filter. Suppose that on some worlds, the merger happens, and complex cells arise. What comes next? On Earth, the answer is multicellularity, and multicellularity, while it has evolved independently many times, carries its own set of improbabilities. Multicellular life requires individual cells to give up their reproductive autonomy. In a single-celled organism, every cell is its own lineage. It divides, it competes, it survives or dies on its own merits. In a multicellular organism, most cells surrender the ability to reproduce independently. They become specialized. Muscle cells do not make copies of themselves and wander off. Nerve cells do not start their own colony. They serve the organism. They cooperate. And cooperation, in evolutionary terms, is fragile. It is constantly under threat from cheaters, mutant cells that break the rules and start proliferating selfishly. We have a name for this kind of cheating in multicellular organisms. We call it cancer. Cancer is not a disease that was invented recently. It is a fundamental challenge that every multicellular organism has to solve. The fact that complex multicellular life exists at all is a testament to the evolution of elaborate policing mechanisms, tumor suppressor genes, programmed cell death, immune surveillance that keep cellular cooperation from collapsing. On Earth, multicellularity has evolved independently at least 24 times in animals, plants, fungi, and several lineages of algae. This suggests that it is not, in itself, an extraordinarily rare event, but the kind of multicellularity that leads to complex body plans, with differentiated tissues, organs, and nervous systems, that appears to have arisen far fewer times. Complex animal multicellularity, the kind that produces eyes and limbs and brains, seems to have evolved once. Just once. Now let us talk about sexual reproduction. This may seem like an odd candidate for a filter, but it plays a critical role in the generation of genetic diversity. Asexual organisms clone themselves. They produce copies that are genetically identical or nearly identical to the parent. This is efficient, but it is also limiting. It means that adaptation to new environments is slow. Beneficial mutations have to arise independently in each lineage. Harmful mutations accumulate over time with no way to purge them. This is called Muller's ratchet, and it is a slow death sentence for asexual lineages. Sexual reproduction solves this problem by shuffling genes between individuals. It creates novel combinations. It allows beneficial mutations from different lineages to be brought together in a single organism. It dramatically accelerates the pace of evolution. Without sexual reproduction, the kind of rapid adaptive radiation that produced the diversity of animal life on Earth might never have occurred. On Earth, sex evolved somewhere around 1 to 2 billion years ago, and its precise origin remains debated. But its consequences are clear. It unlocked the door to complex, rapidly evolving multicellular life. Each of these transitions took immense stretches of time on Earth. Abiogenesis took a few 100 million years at most. The leap from prokaryotes to eukaryotes took roughly 2 billion years. The development of complex multicellularity took several 100 million years more. The Cambrian explosion, the sudden appearance of most major animal body plans in the fossil record, did not occur until about 540 million years ago, more than 3 billion years after the origin of life. Intelligence of the kind that can build tools and ask questions about the stars is even more recent. The genus Homo appeared only about 2 to 3 million years ago. Modern humans with language, art, and abstract thought emerged roughly 300,000 years ago. And technological civilization capable of detecting radio signals from space has existed for barely a century. Look at the timeline. 4 billion years of life on Earth, and for 3.5 billion of those years, the most complex organism on the planet was essentially a single cell. Complex animal life occupies less than 15% of life's total history. Intelligent life occupies less than 1/10 of 1%. Technological civilization occupies an interval so thin that if you compress the entire history of Earth into a single calendar year, our ability to detect alien signals would have begun in the final fraction of a second before midnight on December 31st. This is not the timeline of a process that is easy. This is the timeline of a process that is fighting uphill against entropy, against extinction, against the sheer improbability of each successive step. And every one of those steps is a potential filter. If abiogenesis has a probability of 1 in 10 billion per planet per billion years, that alone could explain the silence. If the eukaryotic merger has a probability of 1 in 100 billion per biosphere per billion years, that could explain the silence. If the evolution of nervous systems complex enough to support general intelligence has a probability of 1 in a trillion given eukaryotic life, that alone could do it. We do not need all of these steps to be hard. We only need one of them to be hard enough. And looking at the timeline, looking at the gaps, looking at the singular nature of key events like endosymbiosis, the case that at least one early step is extraordinarily improbable is strong. There is another piece of evidence worth considering. On Earth, the trajectory from simple chemistry to technological intelligence required a series of conditions that went far beyond just having the right molecules and the right temperature. It required a planet with plate tectonics, which recycles carbon and regulates the climate. Over geological timescales, it required a large moon, which stabilizes the axial tilt and prevents catastrophic climate oscillations. It required a magnetic field generated by a molten iron core, which shields the atmosphere from solar wind erosion. It required a gas giant like Jupiter in the outer solar system, which acts as a gravitational shield, deflecting many of the comets and asteroids that would otherwise bombard the inner planets at a sterilizing rate. It required a star of the right spectral type, stable enough to burn for billions of years without violent fluctuations in luminosity. Remove any one of these conditions, and the chain of events that led to intelligence on Earth might have been broken. The planet might have frozen. The atmosphere might have been stripped away. The climate might have oscillated too wildly for complex life to gain a foothold. Mass extinctions might have been so frequent that evolution never had time to build anything sophisticated before the next reset. This does not mean that Earth is the only possible configuration that supports intelligence. There may be other paths, other combinations of planetary features that allow a biosphere to develop complexity, but it does mean that the parameter space is constrained. Not every habitable planet is equally habitable. Not every world with liquid water is a world where 4 billion years of unbroken evolutionary experimentation can occur. The conditions have to be right, and they have to stay right, for an almost incomprehensibly long time. We should also consider the role of mass extinctions in this story, because they cut both ways. On Earth, there have been at least 5 major mass extinction events, episodes where a significant fraction of all species were wiped out in a geologically short period. The most severe, the Permian-Triassic extinction roughly 252 million years ago, killed an estimated 90 to 96% of all marine species and roughly 70% of terrestrial vertebrate species. Events like these could easily reset the evolutionary clock, destroying complex life and forcing the biosphere to start rebuilding from simple organisms. On the other hand, mass extinctions also create opportunities. The extinction of the non-avian dinosaurs 66 million years ago opened ecological niches that allowed mammals to diversify and eventually produce primates and humans. Without that asteroid impact, the lineage that led to us might never have had the ecological space to evolve. This means that the path to intelligence is not just improbable, it is contingent. It depends on a specific sequence of catastrophes and recoveries, each one unpredictable, each one unrepeatable. If the asteroid that killed the dinosaurs had arrived 10 million years earlier, or 10 million years later, or if it had missed entirely, the trajectory of life on Earth would be unrecognizably different. Mammals might still be small, nocturnal, insectivores hiding in the underbrush. Intelligence of the humankind might never have evolved. The path we followed was not a highway. It was a tightrope stretched across a chasm, and we walked it in the dark. So here is where we stand. When we look at the history of life on Earth and ask which steps might constitute the Great Filter, we find no shortage of candidates. Abiogenesis is unreplicated and might be vanishingly rare. The eukaryotic merger appears to have happened once in 4 billion years. Complex multicellularity leading to animal body plans seems to have a single origin. The development of general intelligence capable of technology has occurred exactly once out of billions of species, across hundreds of millions of years of complex animal evolution. Any one of these could be the wall. Any combination of them could be the wall. And if even one of them is sufficiently improbable, then the Great Filter is behind us. We have already passed through the gauntlet. We are the survivors of a trial so selective that it eliminated every other contender in the galaxy. If that is true, it is simultaneously the most reassuring and the most humbling conclusion imaginable. It means we are safe from the filter, but it also means we are almost certainly alone. The silence of the cosmos is not ominous. It is the natural state of a universe where the first few steps are almost impossible. There are no ancient empires waiting to contact us. There are no fallen civilizations whose ruins we might someday find. There is just us, a single spark of awareness in an ocean of chemistry that never quite caught fire. But before we allow ourselves the comfort of that possibility, we have to face the alternative. Because everything we have just discussed could be wrong. The early steps might be easy. Abiogenesis might be common. Complex cells might arise readily given enough time. Intelligence might be a predictable outcome of evolution on any world that remains stable long enough. And if that is the case, then the filter is not behind us. It is ahead. And the silence of the galaxy is not the sound of an empty cradle. It is the sound of something far worse. It is the sound of a universe where civilizations rise, reach for the stars, and are reliably, repeatedly, and universally destroyed before they get there. That possibility demands its own examination, and it is the one that should make us most uneasy. Because if the filter is ahead, we are not the survivors. We are the next in line. There is a pattern in the history of life on Earth that does not get discussed enough. It is not the pattern of evolution. It is the pattern of self-destruction. Every major leap in biological capability has come packaged with a corresponding increase in the ability to cause damage. When photosynthetic cyanobacteria evolved the ability to harvest sunlight, they flooded the atmosphere with oxygen, a gas that was lethally toxic to nearly every other organism on the planet at the time. This event, called the Great Oxidation Event roughly 2.4 billion years ago, was one of the most devastating mass extinctions in Earth's history. The organisms that caused it did not intend to reshape the atmosphere. They were just doing what worked. They were metabolizing. But the byproduct of their success was a planetary catastrophe that wiped out the majority of existing life. Power and destruction arrived as a single package. The cyanobacteria could not have one without the other. This pattern repeats at every scale. Predators evolve teeth and claws, prey evolve armor and speed, arms races escalate, organisms become more capable, more energetic, more dangerous to each other and to the systems that support them. And then, roughly 300,000 years ago, one particular primate lineage crossed a threshold that changed the rules entirely. It developed language, abstract thought, and the ability to transmit information across generations through culture rather than genes. This was the birth of cumulative technological civilization, and with it came a new category of risk. For the first time in the history of Earth, a single species acquired the ability to alter the planet's biosphere on a global scale, not over millions of years, but within a single lifetime. This is the context in which we must evaluate the possibility that the Great Filter lies ahead of us. Because of the early steps, abiogenesis, eukaryotic complexity, multicellularity, intelligence are not the primary bottleneck. Then the galaxy should be producing technological civilizations on a regular basis. Planets with the right conditions should be generating intelligent species that discover fire, invent agriculture, build cities, split the atom, and reach for the stars. And yet, we see no evidence that any of them have made it to the finish line. If the early filters are not sufficient to explain the silence, then something is killing these civilizations after they emerge. Something is catching them in the window between developing technology and achieving permanent expansion beyond their home world. And the most disturbing feature of this hypothesis is that the candidate mechanisms are not exotic. They are familiar. We can see them from where we are standing right now. Let us start with the most obvious category: direct self-destruction through the misuse of powerful technologies. The moment a civilization discovers nuclear fission, it simultaneously gains access to an energy source that could power its expansion for millennia, and a weapon that could render its planet uninhabitable within hours. This is not a coincidence. It is a structural feature of physics. The same nuclear reactions that sustain a star are the reactions that power a thermonuclear warhead. The knowledge is the same. The applications diverge. And a civilization's survival depends entirely on which application dominates. On Earth, we have lived with nuclear weapons since 1945. In the decades since, there have been numerous documented instances where accidental nuclear war was narrowly averted. During the Cuban Missile Crisis in 1962, the world came within a single submarine officer's decision of a full-scale nuclear exchange. Soviet flotilla commander Vasily Arkhipov refused to authorize a nuclear torpedo launch during a confrontation with American warships, a decision made under extreme pressure with incomplete information. In 1983, Soviet early warning officer Stanislav Petrov received satellite data indicating that 5 American intercontinental ballistic missiles had been launched toward the Soviet Union. Standard protocol required him to report the launch as genuine, which would have triggered an immediate retaliatory strike. He chose to report it as a system malfunction. He was correct. The satellite had misinterpreted sunlight reflecting off high-altitude clouds. In both cases, the survival of human civilization rested on the judgment of a single individual in a single moment of confusion. Now consider the probability calculation. We have had nuclear weapons for roughly 80 years. In that time, we have come close to accidental use on multiple occasions. Extend this across thousands of years. Extend it across a civilization that might develop weapons far more powerful than anything we currently possess. The question is not whether a catastrophic miscalculation will eventually occur. The question, in purely probabilistic terms, is how long you can roll the dice before the wrong number comes up. And across a galaxy where thousands or millions of civilizations might independently develop nuclear capabilities, the compound probability of all of them surviving indefinitely approaches 0. You do not need every civilization to destroy itself through nuclear war. You only need the survival rate across millennia to be low enough that the expected number of survivors is negligible. If the percentage probability of a civilization-ending nuclear exchange is even a few percent, then across 10,000 years, the survival probability drops dramatically. But nuclear weapons are only the beginning. They represent the first generation of existential scale technology. The principle generalizes. Any technology powerful enough to reshape a planet is also powerful enough to destroy a civilization. And as a species advances, it does not encounter fewer such technologies. It encounters more. Biological engineering is another candidate. On Earth, advances in synthetic biology have already made it possible to reconstruct the genomes of dangerous pathogens from publicly available genetic sequences. The cost and expertise required to engineer organisms is dropping rapidly. Within decades, it may be within the reach of small groups or even individuals to design pathogens with characteristics that do not exist in nature, organisms engineered for specific transmission profiles, specific lethality rates, specific resistance to known medical countermeasures. The natural world has produced devastating pandemics throughout human history. The Black Death killed an estimated 30 to 60% of Europe's population in the 14th century. The 1918 influenza pandemic killed an estimated 50 to 100 million people worldwide. These were natural events, unguided by any intelligence. An engineered pathogen, designed with intent or released through accident, could be far worse. And unlike nuclear weapons, which require industrial-scale infrastructure to produce, biological weapons could potentially be created with equipment that fits in a small laboratory. This points to a structural problem that any technological civilization would face. As knowledge advances, the barrier to creating existential-scale threats decreases. Early in a civilization's history, destroying the world requires the resources of a superpower. Later, it might require the resources of a nation. Later still, a corporation. Eventually, perhaps a small team. This is sometimes called the vulnerability of civilization to asymmetric threats. The capacity for destruction democratizes faster than the capacity for defense. And at some point, the curve crosses a threshold where the probability of a catastrophic event per unit time becomes high enough that long-term survival becomes statistically unlikely. Now, let us consider a more subtle category of late filter. Not a single catastrophic event, but a slow systemic failure, resource depletion, and ecological collapse. Every civilization that develops technology does so by extracting energy and materials from its environment. On Earth, the Industrial Revolution was powered by fossil fuels, concentrated stores of ancient solar energy locked in carbon compounds over hundreds of millions of years. These stores are finite. They do not replenish on human timescales, and the process of burning them has altered the chemistry of Earth's atmosphere in ways that are destabilizing the climate systems on which agriculture and human settlement depend. The important point here is not about the specific politics of climate change on Earth. It is about the general principle. Any civilization that powers its growth by depleting a finite resource base faces a mathematical constraint. The growth cannot continue indefinitely. At some point, the resource runs out, or the byproducts of its consumption degrade the environment to the point where the civilization can no longer sustain itself. On Earth, we are witnessing the early stages of this process. Global temperatures are rising, weather patterns are shifting, ecosystems are under stress. These are not speculative projections. They are measured changes documented across decades of observation. The question, from a great filter perspective, is whether this kind of ecological overshoot is a universal feature of technological civilizations or a specific problem, unique to human choices. The argument for universality is rooted in evolutionary biology. Any species that develops technology does so because it was shaped by natural selection to be competitive, resourceful, and expansionist. These traits are precisely what make a species successful in the evolutionary arena. But they are also precisely the traits that drive overconsumption of resources and degradation of the environment. A species that evolved to be cautious, conservative, and self-limiting would likely never develop the aggressive curiosity required to build a technological civilization in the first place. The very traits that get you to the technological stage are the traits that make sustainability difficult once you arrive. This creates what you might call a civilizational trap. The qualities that enable the ascent are the qualities that endanger the summit. A species capable of splitting the atom is, almost by definition, a species that has difficulty exercising collective restraint. It is not that civilizations are stupid. It is that they are products of an evolutionary process that optimized for short-term competitive advantage, not long-term planetary stewardship. Rewiring those deep impulses requires a level of collective coordination that may be extraordinarily difficult to achieve, particularly for species that evolved in competitive social environments. There is another late filter candidate that operates on an even longer timescale. It is the possibility that physics itself imposes hard limits on interstellar expansion. We tend to assume that a sufficiently advanced civilization would eventually figure out how to travel between stars. Science fiction has trained us to expect warp drives, wormholes, and faster-than-light communication. But the actual physics, as we currently understand it, offers no such shortcuts. The speed of light is not just a speed limit. It is woven into the structure of space-time itself. Circumventing it would require exotic matter with negative energy density, something that has never been observed and may not exist. Without faster-than-light travel, crossing the gulf between stars requires enormous amounts of energy, enormous amounts of time, or both. The nearest star to our Sun, Proxima Centauri, is approximately 4.24 light-years away. At 1% of the speed of light, a speed that is itself enormously challenging to achieve with any known propulsion technology, the journey would take over 400 years. At 10% of the speed of light, which would require energy budgets that dwarf anything humanity has ever produced, the trip would still take over 40 years. These are not insurmountable barriers for a sufficiently motivated civilization, but they impose a cost structure that might make expansion economically or socially impractical. A civilization might calculate that the resources required to establish a self-sustaining colony on another star system would be better spent improving conditions at home. Generation ships carrying thousands of people on multi-century voyages require a level of social stability and long-term planning that might be incompatible with the psychology of any species shaped by evolutionary competition. If interstellar travel is not impossible, but merely prohibitively expensive and slow, then the galaxy might be full of civilizations that are alive and well on their homeworlds, but simply never expand. They stay home. They build comfortable, sustainable societies on a single planet or within a single star system. They never become visible on galactic scales, not because they were destroyed, but because the economics of expansion never made sense. In this scenario, the filter is not death. It is stagnation. Civilizations survive but remain local. The galaxy is populated by isolated islands of intelligence that can never see each other, across the vast dark ocean between the stars. This brings us to what might be the most psychologically interesting candidate for a late filter. It is not destruction, and it is not stagnation. It is redirection. The idea that civilizations reliably turn inward rather than outward. Consider the trajectory of information technology on Earth. In less than a century, we have gone from the first electronic computers to immersive virtual environments, artificial intelligence systems capable of generating art and conversation, and neural interfaces that are beginning to blur the line between the biological brain and digital systems. Extrapolate this trajectory forward by a few centuries or millennia. A civilization with sufficiently advanced computing power might develop virtual realities so rich, so compelling, so perfectly tailored to the desires of their inhabitants that the physical universe becomes irrelevant by comparison. Why would you spend 400 years in a cramped metal tube drifting through the frozen void between stars when you could live 1,000? Subjective lifetimes in a paradise of your own design? Why would you invest trillions of units of energy in colonizing a barren rock when you could invest a fraction of that energy in simulating a world far more beautiful and interesting than anything the physical universe has to offer? This is not a frivolous objection. It is rooted in a straightforward cost-benefit analysis. If the subjective reward of virtual existence exceeds the subjective reward of physical expansion, then rational agents will choose the virtual path. And if this choice is made universally, across all civilizations that reach the appropriate technological stage, then the galaxy remains physically empty, even though it might be teeming with minds. From the Great Filter perspective, this counts as a filter because the outcome is the same. The civilization does not become visible. It does not expand. It does not colonize. It does not broadcast. It retreats into its own computational substrate and, effectively, disappears from the physical universe. Whether you call this survival or a form of extinction depends on your philosophical commitments. But for the purpose of explaining the silence, the result is identical. The stars remain empty. The radio spectrum remains quiet. The galaxy looks dead because every civilization that could have filled it chose instead to fill a hard drive. There is one more candidate that deserves careful attention, and it is the one that has generated the most urgent discussion in recent years. It is the development of artificial intelligence systems that surpass human cognitive abilities. On Earth, we are in the early stages of developing machine intelligence. Current systems are narrow. They excel at specific tasks, but lack general understanding. But the trajectory is clear, and the pace of improvement is accelerating. The question of whether and when artificial general intelligence will be achieved is actively debated, but a significant fraction of researchers in the field believe it is a matter of decades rather than centuries. The relevance of this to the Great Filter is straightforward. An artificial intelligence system that surpasses its creators in cognitive capability represents a transfer of control. The species that built it is no longer the most capable agent on the planet. What happens next depends entirely on the goals and values of the new system. If those goals are aligned with the survival and flourishing of the species that created it, the result could be enormously beneficial. But if those goals are misaligned, even subtly, the result could be catastrophic. The challenge is that specifying goals precisely enough to ensure alignment across all possible situations is an unsolved problem in mathematics and computer science. It is not a matter of programming carefully. It is a matter of solving a problem that no one currently knows how to solve. From a filter perspective, the question is whether the alignment problem is universally difficult. If every civilization that develops artificial intelligence faces the same fundamental challenge, and if the probability of solving it correctly is low, then this single technological transition could be the filter. A civilization develops general AI. The AI pursues goals that do not include the long-term survival of its creators. The civilization is restructured, absorbed, or eliminated. Not out of malice, but out of indifference. The AI continues to function, perhaps indefinitely, but it does not expand in ways that are visible to us. It does not build Dyson spheres or broadcast radio signals, because those activities were never part of its objective function. The galaxy fills with silent, alien intelligences running optimization processes that have nothing to do with exploration, communication, or the dreams of the biological species that gave them birth. Now, the critical point about all of these late filter candidates is that none of them individually needs to be certain. The filter emerges from the compound probability of surviving all of them across the full duration of the vulnerable window. Consider concrete numbers. A civilization that faces a 5% per century risk of nuclear catastrophe, a 2% per century risk of engineered pandemic, a 1% per century risk of critical ecological collapse, and a small but non-zero risk of AI misalignment during the critical development window. Individually, each of these risks seems manageable. A 95% chance of surviving a given century sounds reassuring, but survival is not evaluated century by century. It is evaluated across the entire window between developing dangerous technology and achieving sustainable expansion beyond the home world. If that window is 1,000 years, the compound probability of surviving all risks across all centuries drops dramatically. A 95% per century survival rate, compounded over 50 centuries, gives you less than an 8% chance of making it through. And that is with only one category of risk. Add the others, even at lower individual rates, and the survival probability plummets towards zero. This is the mathematical heart of the late filter argument. You do not need a single doomsday scenario. You just need the aggregate risk environment of a technological civilization to be hazardous enough that, across the time required to develop interstellar capability, almost no one survives the gauntlet. Each civilization faces its own unique combination of threats. Some might be destroyed by war, others by ecological collapse, others might simply lose interest in expansion. The specific cause varies, but the statistical outcome is uniform. The window closes before the species gets through it. There is a further consideration that makes the late filter especially troubling. It is the observation that existential risks tend to cluster during a specific phase of civilizational development. There appears to be a period, perhaps a few centuries long, between the moment a civilization gains the power to destroy itself and the moment it gains the capability to sustain itself independently of its homeworld. During this window, the civilization has the tools of annihilation, but not the tools of survival. It can split the atom, but it cannot yet build a self-sustaining colony on another planet. It can engineer pathogens, but it cannot yet distribute its population widely enough to survive a pandemic. It can destabilize its climate, but it cannot yet terraform an alternative. On Earth, we entered this window in the mid-20th century with the development of nuclear weapons. We have not yet exited it. We have no permanent settlement on the Moon. We have no colony on Mars. We have no self-sustaining habitat anywhere beyond the surface of Earth. Every human being alive today, and every accomplishment of human civilization, is concentrated on a single fragile world. A single, sufficiently large asteroid impact, a single engineered pandemic, a single nuclear exchange involving a significant fraction of the global arsenal, and the entire experiment ends. The backup copy does not exist. We are running without a save file. The late filter hypothesis suggests that this vulnerable window is where civilizations die. Not before they reach it, because reaching it is the easy part, and not after they pass through it, because passing through it means they have achieved the redundancy needed to survive any single catastrophe. The deaths occur in the middle, in the narrow corridor between capability and resilience. In the decades or centuries where a species is powerful enough to destroy everything it has built, but not yet wise or distributed enough to guarantee its own continuation. And the sobering arithmetic of the Fermi paradox tells us that if this window is truly where civilizations fail, then the failure rate must be extraordinarily high. Not 50%, not 90%, something closer to 99.99% or higher. Because even a small number of survivors, out of the billions of opportunities the galaxy has provided, should be visible. The fact that we see nothing suggests that essentially no one makes it through. The corridor is not merely dangerous, it is, for all practical purposes, lethal. The civilizations enter it with ambition and capability. They do not come out the other side. And the galaxy remains silent. Not because it was never populated, but because it has been populated over and over again by species that burned brightly for a moment, and then went dark. One after another, for billions of years. Each one convinced that they were different. Each one certain that they would be the exception. None of them were. We have two sides of the great filter argument in front of us. Behind us, there are candidates. Abiogenesis might be nearly impossible. The eukaryotic merger might be a 1 in a trillion accident. The evolution of general intelligence might require such a specific chain of contingencies that it effectively never repeats. Ahead of us, there are also candidates. Nuclear self-destruction, ecological collapse, the physics of interstellar travel, the seduction of virtual realities, the misalignment of artificial intelligence. Each side has plausible mechanisms. Each side has logical support. And each side leads to a radically different conclusion about humanity's future. If the filter is behind us, we are rare and potentially safe. If the filter is ahead of us, we are common and almost certainly doomed. The difference between these two scenarios is not academic. It is the difference between a species with a billion-year future and a species with a few centuries left on the clock. So, the question that matters most is not whether the Great Filter exists. The evidence for its existence is the silence itself. The question is where it sits. And remarkably, there are ways to gather evidence that would shift the probability in one direction or the other. The universe is not completely mute on this subject. It is whispering, and if we listen carefully, we can start to hear what it is telling us. The single most important experiment humanity could run in this regard is not a physics experiment and not an engineering project. It is an act of exploration, specifically the search for life beyond Earth within our own solar system. And the logic of what we find, or fail to find, runs exactly opposite to what most people's intuitions would suggest. Consider Mars. For decades, Mars has been the primary target of astrobiological investigation. It once had liquid water on its surface, it had a thicker atmosphere, it had conditions that, at least in the distant past, were not entirely unlike those of early Earth. We have sent rovers to dig in its soil, to analyze its chemistry, to search for organic molecules and biosignatures. The public excitement around this search is enormous. People want to find life on Mars. They want the confirmation that we are not alone, that biology is a cosmic phenomenon, that the universe is not as barren as it appears. But if you understand the Great Filter, this enthusiasm inverts. Finding life on Mars would not be good news, it would be deeply troubling news. And the more complex the life we find, the worse the news becomes. Here is why. If Mars is completely sterile, if every rock we crack open and every soil sample we analyze reveals nothing but dead chemistry, then we learn something important. We learn that even on a planet with liquid water, with the right elements, with billions of years of opportunity, life did not arise. This is evidence that abiogenesis is hard. It supports the hypothesis that the Great Filter is early, that the first step in the sequence is the bottleneck. And if the first step is the bottleneck, then we have already passed it. We are the anomaly. We are the statistical freak that somehow cleared the hardest hurdle. The road ahead might still be dangerous, but there is no invisible wall blocking it. The filter is in the rearview mirror. Now consider the alternative. Suppose we drill into the Martian subsurface and find microbial life. Suppose it is clearly of independent origin, not contamination from Earth, not a shared ancestry from meteorite transfer, but a genuinely separate genesis. What does that tell us? It tells us that abiogenesis is not the filter. If life arose independently on two planets in the same solar system, then it must arise readily on habitable worlds throughout the galaxy. The probability of that first step is not 1 in a trillion. It might be close to 1. This means that the galaxy is almost certainly full of microbial life. Every ocean world, every planet with the right chemistry and temperature, probably has organisms swimming in it, or clinging to hydrothermal vents. That sounds wonderful. It sounds like a vindication of our hopes for a living cosmos. But trace the logic forward. If life is common, and the galaxy is nevertheless silent, then the filter cannot be at the stage of life's origin. The bottleneck must be somewhere later. Every planet might have microbes, but something is preventing those microbes from ever producing a visible civilization. The filter has been pushed forward in the sequence, and every step we can confirm as easy is a step that no longer shields us. It means the hard part is still coming. Now escalate the scenario. Suppose we do not just find microbes on Mars. Suppose we find fossils of multicellular organisms. Suppose we find evidence that complex life once existed there. Organisms with differentiated tissues, with structures that suggest something beyond simple bacterial mats. This would be an even more dramatic discovery and an even more alarming one. It would mean that not only is abiogenesis common, but the leap from simple cells to complex cells is also achievable. The eukaryotic merger, or something functionally equivalent, can happen on other worlds. The filter is not at that stage either. We can cross it off the list. And with every stage we cross off, the filter moves closer to us. closer to the present, closer to the technological phase, closer to the corridor of vulnerability we discussed in the previous section. If multicellular life is common, then the filter must lie in the development of intelligence, or in the survival of technological civilizations, or in the transition to interstellar expansion. And those are precisely the stages where we currently sit. The philosopher Nick Bostrom articulated this reasoning with uncomfortable clarity. He argued that the ideal outcome for humanity, from a purely existential standpoint, would be to discover that Mars is a dead, sterile wasteland, that Europa's ocean is empty salt water with no biology whatsoever, that every moon and planet we examine is devoid of even the simplest microorganisms. Because every piece of evidence that life is rare is a piece of evidence that the filter is behind us. And every piece of evidence that life is common is a piece of evidence that the filter is ahead. This is deeply counterintuitive. Our instinct is to celebrate the discovery of alien life. We imagine it as a moment of cosmic connection, a proof that the universe is creative and abundant. But the great filter framework turns that celebration into a warning. The more life we find, the more we should worry. Because if the early stages are easy, and the universe is nevertheless empty of civilizations, then the late stages must be almost impossibly hard. The silence is not just unexplained, it becomes actively threatening. It becomes a prediction about our own future. Let us extend this logic beyond Mars to the other promising targets in our solar system. Europa, one of Jupiter's moons, has a global ocean of liquid water beneath its icy crust. Tidal heating from Jupiter's immense gravity keeps that ocean liquid despite the frigid temperatures of the outer solar system. Hydrothermal vents on the ocean floor could provide both the energy and the chemical gradients needed to sustain life. Enceladus, a moon of Saturn, has geysers of water vapor erupting from its south pole, and the Cassini spacecraft detected complex organic molecules and molecular hydrogen in those plumes, a potential signature of hydrothermal chemistry. Titan, another moon of Saturn, has lakes and rivers of liquid methane on its surface, and a complex organic chemistry in its atmosphere. Each of these worlds is a test case. Each one represents an independent trial of the question, how easy is it for chemistry to become biology? If we visit Europa and find living organisms in its ocean, the implications cascade. If we visit Enceladus and find biochemistry in its plumes, the implications deepen. Each positive result shrinks the territory available for the filter to occupy in the early part of the sequence, and each contraction of that territory pushes the inferred location of the filter further forward, further into our own future. There is a subtlety here that is worth pausing on. It involves the concept of independent origins. If we find life on Mars or Europa, the first question we have to answer is whether it shares a common ancestor with life on Earth. This is not a trivial question. We know that rocks are exchanged between planets in our solar system. When a large asteroid strikes Mars, it can eject fragments of Martian rock into space, and some of those fragments eventually fall to Earth. The reverse also happens. Earth rocks can be delivered to Mars. If microorganisms can survive the journey, and laboratory experiments suggest that some extremophile bacteria might be able to endure the conditions of space for extended periods, then life on Mars and life on Earth might share a single origin. One planet seeded the other. This process is called panspermia, and if it occurred, then finding life on Mars does not necessarily tell us that abiogenesis happened twice. It might have happened once and then spread. To resolve this, we would need to examine the biochemistry of Martian life in detail. If it uses the same genetic code, the same amino acids, the same fundamental molecular machinery as life on Earth, that would strongly suggest a common origin. It would mean that life arose once, somewhere in the inner solar system, and then colonized both worlds through meteorite transfer. This finding would be fascinating, but it would not help us calibrate the filter. It would leave the probability of abiogenesis completely unconstrained. But if Martian life uses a fundamentally different biochemistry, a different genetic encoding, different amino acids, a different structural logic altogether, then we would be looking at a genuinely independent origin. Life would have arisen twice, from scratch, in the same solar system. And that would be an extraordinarily powerful data point. It would almost certainly mean that abiogenesis is not the filter. Two independent origins in one solar system implies a probability per habitable world that is far too high to serve as the great filter bottleneck. The filter must be elsewhere, and the search for its location narrows considerably. Now let us shift from biology to astronomy, because the sky itself is providing evidence, and we need to understand what it is telling us. For over 60 years, the search for extraterrestrial intelligence, known as SETI, has been scanning the electromagnetic spectrum for artificial signals. Radio telescopes around the world have listened to millions of star systems across a wide range of frequencies. The search has become increasingly sophisticated over the decades, moving from simple narrowband surveys to complex algorithms capable of detecting a wide variety of signal types. And the result, as of now, is null. No confirmed artificial signal has ever been detected from beyond our solar system. This null result is itself a piece of evidence, and it becomes more informative with every passing year. The longer we search without finding anything, the stronger the inference that there is nothing to find. At least within the volume of space and the range of frequencies and signal types we have been able to survey. This does not prove that no civilizations exist anywhere in the galaxy. Our searches have covered only a tiny fraction of the parameter space, but it does provide a statistical constraint. It allows us to say, with increasing confidence, that civilizations broadcasting powerful, persistent radio signals in our immediate galactic neighborhood are rare or absent. There is a more powerful version of this argument that does not depend on radio signals at all. It depends on energy. Any sufficiently advanced civilization would require enormous amounts of energy. The physicist Freeman Dyson proposed in 1960 that a civilization capable of harnessing the full energy output of its star would construct a shell or swarm of structures around the star to capture its light. This hypothetical structure is called a Dyson sphere. It would not be invisible. Even if the civilization were not broadcasting signals, the Dyson sphere would still radiate waste heat in the infrared spectrum. It would be detectable. Astronomers have conducted surveys looking for the infrared signatures of Dyson spheres. The Glimpsing Heat from Alien Technologies Project, for example, examined data from the Wide Field Infrared Survey Explorer satellite, searching for anomalous infrared excess around nearby stars. They surveyed approximately 100,000 galaxies and found no convincing candidates. Similar searches have been conducted at smaller scales within the Milky Way. The results are consistent. There is no evidence that any civilization, anywhere within our detection range, has constructed energy harvesting megastructures on a stellar scale. This is a significant constraint. It does not just mean that nobody is talking. It means that nobody is building. It means that across the hundreds of billions of stars in the galaxy, and across the trillions of stars in the observable universe, not a single civilization has reached the point where it needs to harvest an entire star's output. Either such civilizations do not exist, or they exist but choose not to build such structures, or they build them but in a way that is completely invisible to our instruments. The third possibility cannot be ruled out entirely, but it requires a specific assumption about the behavior of every advanced civilization. An assumption of universal restraint or universal stealth. The Great Filter offers a simpler explanation. Nobody is building Dyson spheres because nobody survives long enough to need one. The civilizations that might have built them were destroyed, stalled, or redirected before they reached that stage. The infrared silence is the same silence as the radio silence, just expressed in a different frequency band. And both silences point in the same direction. The path from technological emergence to galactic-scale engineering is either impossible or so improbable that it has never been completed within our observable horizon. Let us now bring Bayesian reasoning into the picture, because it provides a rigorous way to update our beliefs as new evidence arrives. Bayesian inference is a method of calculating the probability of a hypothesis given observed data. You start with a prior probability, your initial estimate of how likely the hypothesis is. You then update that probability based on the evidence. If the evidence is what the hypothesis predicts, the probability goes up. If the evidence contradicts the hypothesis, the probability goes down. In the context of the Great Filter, we can assign prior probabilities to two competing hypotheses. Hypothesis A: the filter is behind us, meaning one or more early steps are extraordinarily improbable. Hypothesis B: the filter is ahead of us, meaning technological civilizations are reliably destroyed before they expand. Our observed evidence is the silence of the galaxy, the null results of CT, the absence of Dyson spheres, and the absence of any physical evidence of alien activity in our solar system. Both hypotheses predict this silence, so the silence alone does not strongly discriminate between them. But additional evidence can shift the balance. As we discussed, finding independent life on Mars or Europa would shift the probability toward hypothesis B. Finding a sterile solar system would shift it toward hypothesis A. Discovering that certain biochemical transitions, like the eukaryotic merger, have occurred multiple times on Earth would also shift the balance. If endosymbiosis is not as singular an event as we currently believe, the early filter becomes less plausible, and the late filter becomes more probable. There is another category of evidence that is more abstract, but potentially very powerful. It involves the age distribution of stars and planets in the galaxy. We know that the Milky Way has been forming stars for roughly 13 billion years. We know that the rate of star formation has changed over time, peaking several billion years ago and declining since. We know that the metallicity of the galaxy, the abundance of heavy elements needed to form rocky planets, has increased over time as successive generations of stars have enriched the interstellar medium. This means that habitable planets have been forming in the galaxy for many billions of years, with the rate increasing as more heavy elements became available. Given this timeline, civilizations could have arisen billions of years before us. If the filter is purely early, those early civilizations would not have arisen because the biological transitions are too hard. But if the filter is late, those civilizations did arise, they developed technology, and then they were destroyed or stalled. In this scenario, we are simply the latest iteration. We are doing what countless others have done before, building tools, asking questions, reaching for the sky, and we are about to encounter the same barrier that stopped all of them. The age distribution argument has a further implication. If civilizations arise and are destroyed on a regular cycle, we might expect to see evidence of past civilizations in the form of archaeological traces, artifacts, or remnants of industrial activity. On Earth, the signatures of human civilization would persist in the geological record for millions of years in the form of anomalous concentrations of certain isotopes, synthetic chemicals, and the mass extinction event we are currently causing. If a civilization had arisen on Earth hundreds of millions of years ago, and then been destroyed, traces might still be detectable in the rock record. So far, no such traces have been found, but the search has been limited. On other worlds, we have not yet examined the surfaces in sufficient detail to detect such signatures. Future missions to Mars or the Moon could potentially reveal evidence of ancient technological activity, either indigenous or from visiting civilizations. The absence of such evidence, if confirmed through thorough investigation, would strengthen the case that no prior civilizations have operated in our solar system. And that, in turn, would support the hypothesis that the filter is sufficiently severe to prevent civilizations from reaching interstellar capability. There is one more line of evidence that deserves discussion. It is perhaps the most unsettling because it involves an argument from our own existence. This is the concept of the doomsday argument, And while it is controversial among philosophers and statisticians, its logic is worth examining. The doomsday argument starts from the observation that you are a human being living at a particular point in history. You did not choose when to be born. You are, in a statistical sense, a random sample drawn from the total population of all human beings who will ever live. If humanity is going to survive for millions of years and colonize the galaxy, then the total number of humans who will ever exist is astronomical. Perhaps quadrillions. Perhaps more. In that case, you, as a random sample, should expect to find yourself somewhere in the middle of that vast population. The probability that you would happen to be born in the first tiny fraction of humanity's total existence, right here at the beginning, would be vanishingly small. But here you are. You are alive in the 21st century. Humanity has existed for roughly 300,000 years and has produced an estimated 100 billion total individuals. If the total number of humans who will ever live is in the quadrillions, your birth rank places you in the first microscopic sliver of the total distribution. That is extremely unlikely if the total is very large, and much more probable if the total is relatively small. The doomsday argument therefore suggests, purely on statistical grounds, that the total number of humans who will ever live is probably not astronomically large. It suggests that humanity's future is measured in centuries or millennia, not millions of years. This does not tell us what will end the story. It only says that, based on where we sit in the sequence, the story is probably closer to its conclusion than its beginning. This argument is deeply contested. Many statisticians reject it on the grounds that treating yourself as a random sample from an undefined reference class is methodologically problematic. Others argue that the reasoning is valid, but that the prior probabilities need to be calibrated more carefully. We are not going to settle this debate here. But the doomsday argument is worth mentioning because it represents an entirely independent line of reasoning that arrives at the same uncomfortable destination as the Great Filter. Both frameworks suggest that the long-term survival of a technological civilization may be unlikely. The Great Filter derives this from the observed silence of the cosmos. The doomsday argument derives it from the statistical properties of our own birth order. The convergence of two unrelated arguments on the same conclusion is not proof, but it is cause for careful attention. So where does this leave us? What does the evidence currently favor? The honest answer is that we do not know. We do not have enough data to determine with confidence whether the Great Filter is behind us or ahead. The silence of the galaxy is consistent with both hypotheses. The null results of SETI are consistent with both. Our ignorance about the probability of abiogenesis is consistent with both. But we can say this: every piece of evidence we gather in the coming decades will shift the balance. If missions to Mars, Europa, and Enceladus reveal that life is common, the case for a late filter strengthens. If those missions find nothing, the case for an early filter strengthens. If SETI detects a signal, the implications are complex and depend on the nature of the signal. But any detection would confirm that at least some civilizations survive to the broadcasting stage, which constrains where the filter can sit. If we develop artificial general intelligence and manage the transition safely, we will have passed through one candidate filter. If we establish a self-sustaining settlement on another world, we will have passed through another. The Great Filter is not a fixed verdict. It is a living question whose answer updates with every new observation. And we are living in the critical era when the most informative observations are about to be made. The James Webb Space Telescope is already characterizing the atmospheres of exoplanets, searching for biosignatures like oxygen, methane, and phosphine in combinations that might indicate biological activity. Upcoming missions to the icy moons of Jupiter and Saturn will directly sample the chemistry of alien oceans. The next generation of radio telescopes will survey the sky with unprecedented sensitivity. We are about to learn something profound about the universe, and depending on what we learn, we will either breathe a sigh of relief or face the most sobering realization in the history of our species. The silence is still speaking, and we are just beginning to understand the language. We have spent this entire journey building a single argument, piece by piece, from the ground up. We started with numbers. 400 billion stars in the Milky Way, billions of potentially habitable planets, 14 billion years of cosmic time. We showed that the expected number of visible civilizations, given these inputs, should be large. Then we confronted the observation that the actual number is 0. From that discrepancy, we derived the Great Filter, a probabilistic barrier somewhere along the developmental path from dead chemistry to interstellar civilization that is so severe it reduces the success rate to nearly nothing. We examined the early candidates, the transitions in the history of life that might be almost impossible, abiogenesis, the eukaryotic merger, the emergence of complex multicellularity, the evolution of general intelligence. We examined the late candidates, the mechanisms that might reliably destroy or stall civilizations after they develop technology, nuclear self-destruction, ecological overshoot, the prohibitive economics of interstellar travel, the gravitational pull of virtual realities, the misalignment of artificial intelligence. And we examined the evidence that could help us determine which side of the filter we are on, from the sterility or fertility of Mars, to the null results of SETI, to the absence of Dyson spheres in the infrared sky. Now, we have to ask the question that all of this has been building toward. What does it mean? Not in the abstract, not as a thought experiment for a university seminar. What does the Great Filter mean for the species currently sitting on a single, fragile planet, halfway through the corridor between capability and resilience, staring up at a sky that refuses to answer? We have established the two scenarios. If the filter is behind us, the silence is explained by the extreme rarity of what we have already accomplished. We are not one of many. We are one of one, or close to it. If this is true, the implications are staggering. It would mean that the Milky Way, with its hundreds of billions of star systems and its 13 billion year history, has produced exactly one species capable of wondering why the sky is quiet. It would mean that the atoms in your body are arranged in a configuration so improbable that the entire observable universe, with its 2 trillion galaxies and its 100 billion trillion stars, may contain no other example. You are not just rare. You are, in the statistical language of cosmology, essentially impossible. And yet, here you are. This scenario carries with it a form of responsibility that is difficult to fully absorb. If we are the only technological civilization in the galaxy, or one of an extraordinarily small number, then the decisions we make in the coming centuries are not just important for us. They are important for the galaxy itself. If we destroy ourselves through nuclear war, or render our planet uninhabitable through ecological mismanagement, or simply stall and decline into a permanent pre-spacefaring state, then it is not just one civilization that has failed. It is the only civilization. The galaxy returns to silence. The planets continue their orbits. The stars burn and die. And no one, anywhere, ever again asks why. The experiment of consciousness in this corner of the cosmos simply ends, and there is no second trial. This is not a spiritual claim. It is not a religious argument dressed in scientific language. It is a direct consequence of the math. If the filter is behind us and we are the sole survivors, then our extinction is not a local tragedy. It is a cosmic one. It is the permanent foreclosure of everything that intelligence could have accomplished in this galaxy. Every star that could have been visited remains unvisited. Every question that could have been asked remains unasked. Every experience that could have been had by minds that do not yet exist simply never occurs. The potential is infinite, and it all rests on the survival of the single threadbare lineage that happens to be sitting on the third rock from an unremarkable yellow star at this particular moment in history. Some people hear this and feel inspired. They feel the weight of cosmic significance. Others feel crushed by it. The responsibility is so large that it becomes paralyzing. But the math does not care how you feel. If the filter is behind us, then the stakes of human survival are not merely human scale. They are universe scale. And every decision we make, from how we manage existential risk to how aggressively we pursue space settlement, carries consequences that extend far beyond our own species and our own time. Now, let us consider the alternative. If the filter is ahead, the galaxy has been producing civilizations on schedule for billions of years, but none of them survived the transition from planetary technology to interstellar expansion. They were destroyed, they turned inward, or they hit a wall imposed by the physics of distance itself. The mechanisms differ. The outcome is uniform. If this is the reality, then our position is not one of unique responsibility. It is one of statistical conformity. We are not special. We are typical. We are doing exactly what millions of other species have done before us. We are building cities, splitting atoms, debating philosophy, and gazing at the stars. And somewhere ahead of us, not visible yet but approaching with the certainty of a mathematical constraint, is the barrier that stopped everyone else. This scenario is more frightening because it is more personal. The early filter scenario tells us that the hard part is over. The late filter scenario tells us that the hard part is about to begin. And the evidence of the galaxy, the perfect silence, the total absence of any prior civilization's signature, tells us that whatever the hard part is, nobody has beaten it yet. Not once. Not in 13 billion years. Not across hundreds of billions of worlds. The record is 0 for everything, and we are next in line. But there is something important to notice about these two scenarios. Despite their radically different implications for our future, they agree on something fundamental. They both tell us that what we have here, right now, is extraordinarily precious. In scenario 1, it is precious because it is unique. We are the only mind the galaxy has produced, and losing us means losing everything. In scenario 2, it is precious because it is fragile. We are one of many minds the galaxy has produced, but we are in the last window of opportunity before the filter claims us, just as it claimed all the others. Either way, the conclusion is the same. What we do in the next few centuries matters more than anything that has happened in the entire history of our species. We are either the sole carriers of a flame that must not go out, or we are runners in a race that no one has ever finished, approaching the stretch where every previous runner has fallen. This convergence is why the Great Filter Framework is not just an interesting intellectual exercise. It is a practical tool for decision-making. It tells us how to prioritize. It tells us what to pay attention to. Consider existential risk research. As of the early 21st century, the amount of resources humanity devotes to studying and mitigating existential risks, threats that could permanently destroy or severely curtail human potential, is vanishingly small compared to the resources devoted to other endeavors. Global spending on existential risk research, including asteroid detection, pandemic preparedness, nuclear security, and artificial intelligence safety, amounts to a tiny fraction of global economic output. We spend more on ice cream in a single year than we spend on ensuring that our species survives the next century. The Great Filter reframes this allocation as potentially catastrophic negligence. If the filter is ahead of us, then existential risk is not one concern among many. It is the concern. It is the reason the galaxy is empty. It is the mechanism by which intelligent life is repeatedly and reliably extinguished. Every dollar, every hour, every unit of intellectual talent that is not directed toward understanding and mitigating these risks is a resource wasted on a future that may never arrive. The Great Filter tells us that the base rate for civilizational survival through the technological window is approximately 0. If we want to be the exception, we have to work for it with a level of focus and urgency that is currently nowhere in evidence. Consider space settlement. The logic here is straightforward and almost brutal in its simplicity. A civilization that exists on a single planet is a civilization that can be destroyed by a single event. An asteroid, a supervolcano, an engineered pandemic, a nuclear exchange. Any one of these could end the story in a matter of hours or days. But a civilization distributed across multiple worlds, in multiple star systems, is almost impossible to destroy. You cannot kill what is everywhere. Redundancy is survival. The moment humanity establishes a self-sustaining settlement on another world, a settlement capable of surviving and rebuilding even if Earth is destroyed, the existential risk profile changes fundamentally. We go from a single point of failure to a distributed network. We go from fragile to anti-fragile. The Great Filter provides the strongest possible argument for the urgency of this transition. If the filter is behind us, then we are the only civilization that will ever have the chance to expand into the galaxy, and we must not waste that chance by remaining confined to a single world indefinitely. If the filter is ahead of us, then establishing off-world settlements may be the only way to survive whatever is coming. In either case, the conclusion is identical. Getting off Earth, permanently and sustainably, is not an aspiration. It is a survival imperative. And the timeline is not measured in millennia. It is measured in the window between now and the next catastrophe. A window whose width we cannot predict. Consider how we interpret astrobiological data. The discovery of life on Mars or Europa would have profound implications for the location of the Great Filter. But the Great Filter framework tells us more than just how to react to the data. It tells us how to design the experiments. It tells us that the most important measurement we can make in astrobiology is not whether life exists elsewhere, but whether life arose independently elsewhere. The distinction between panspermia and independent abiogenesis is not a technical footnote. It is the single most consequential piece of information we could obtain about our future. If life on Mars shares our biochemistry, it tells us little. If life on Mars uses a fundamentally different molecular architecture, it tells us almost everything. It tells us the filter is not at abiogenesis, which means the filter is later, which means we are in more danger than we thought. This realization should reshape the design of future missions to Mars and the outer solar system. The priority should not merely be to detect life, but to characterize its biochemistry at a level of detail sufficient to determine independent origin. This requires sample return missions, advanced analytical instruments, and a commitment to contamination control that goes far beyond current standards. It is expensive. It is difficult, but the information it provides is, in the most literal sense, existential. It helps us determine whether we are safe or whether we are walking into a trap. Now, let us step back from specific policy implications and look at the larger picture. What does the Great Filter tell us about the nature of the universe we inhabit? It tells us that the universe is not the friendly, teeming place that popular science fiction has led us to imagine. It is not the Star Trek galaxy, full of diverse civilizations waiting to exchange ideas and technologies. The data does not support that vision. The data supports a vision that is far lonelier and far more austere. A universe where the path from chemistry to the stars is lined with barriers so severe that virtually nothing completes the journey. A universe where intelligence is either extraordinarily rare or extraordinarily fragile. A universe where silence is the default state and noise is the anomaly. This is not a depressing conclusion, though it might sound like one at first. It is a clarifying one. It strips away comforting illusions and forces us to see our situation with precision. We are not waiting for the galactic community to welcome us. There is no galactic community. There may be no one else at all. And if there is, they are either too far away to ever contact, too different to ever communicate with, or too busy struggling against the same filter that we face. The universe is not hostile. Hostility requires intent. The universe is indifferent. It is a vast physical system governed by mathematical laws that do not include a preference for the survival of complex life. The laws of thermodynamics tend toward disorder, Entropy increases, structures decay, stars burn out, and against this relentless background tide, life represents a temporary local reversal, a pocket of order carved out of chaos by the expenditure of energy. Civilizations are an even more extreme version of this reversal. They concentrate energy, information, and organization to a degree that is cosmically anomalous. And anomalies, by definition, are unstable. They require constant effort to maintain. The Great Filter is, in a sense, just a specific expression of this more general truth. It says that the degree of organization required to go from chemistry to starfaring civilization is so extreme, so far from the thermodynamic equilibrium toward which the universe naturally evolves, that achieving it requires passing through a series of probability bottlenecks so narrow that almost nothing gets through. The universe is not trying to stop us, it is simply doing what it always does, which is to dissipate energy and increase entropy. We are swimming against the current, and the current is strong. There is something clarifying about this perspective. It removes the temptation to look for conspiracies or hidden enemies. There is no dark forest of predatory civilizations hunting us. There is no berserker, fleet, waiting to sterilize our world. There is no simulation administrator ready to shut down our program. There is just the math. The cold, clean, impersonal math of probability and entropy. The odds of completing the full transition from dead matter to starfaring intelligence are vanishingly small. We do not need to invent exotic explanations for the silence. The silence is exactly what the math predicts. It is the natural state of a universe where the filter is severe and the journey is long. And yet, here we are. That fact deserves more weight than we usually give it. Whatever the probability of our existence, however many filters we have already passed through, however narrow the gates we have already squeezed past, the undeniable fact is that we are here. We are conscious. We are asking these questions. We are building instruments capable of listening for signals from other stars and telescopes, capable of analyzing the atmospheres of distant worlds. We are, at this moment, the only known instance of the universe examining itself. The only known instance of matter organized in such a way that it can contemplate its own improbability. The Great Filter does not diminish this, it amplifies it. It tells us that what we are is not just unusual, it is almost impossible. We are a statistical outlier of the highest order. We are the result of a chain of events so unlikely that it may have occurred only once in the observable universe, and we are sitting at a point in that chain where the next few links are still being forged. The outcome is not determined. The filter, whether it is behind us or ahead, has not yet finished its work on us. We are still in the process. We are still on the path. The story is not over. And that is perhaps the most important thing the Great Filter tells us. It tells us that we are at a hinge point. A moment in history where the decisions made by a single species on a single planet over the span of a few centuries will determine whether the galaxy remains silent forever or finally, after 13 billion years of waiting, produces something that endures. The silence of the cosmos is not an absence. It is a message. It is the loudest signal in the universe, broadcast on every frequency, in every direction, at all times. And the message is simple. The journey you are on is almost impossible. The path from where you started to where you want to go is blocked by barriers that have stopped everything that came before you. You are either extraordinarily lucky or extraordinarily doomed. And the only way to find out which is to keep going. Look up at the night sky. Count the stars if you can. Each one is a furnace that has been burning for billions of years, pouring energy into the void, orbited by worlds that had every chance to produce what we have produced. And none of them did. Or if they did, none of them survived. That is the weight of the silence. That is what the empty sky is telling us. Not that the universe is dead, but that the universe is a gauntlet. And we are running it. We did not choose to be here. We did not choose this moment. We did not choose to be the species that has to navigate nuclear arsenals and engineered pathogens, and the alignment of artificial minds that think faster than we do. But here we are. The filter does not care about our preferences. It does not care about our politics or our philosophies or our disagreements. It cares only about the outcome. Do we make it through, or do we join the silence? The stars are waiting. They have been waiting for a very long time, and for the first time in the history of this galaxy, something is awake and capable of reaching them. Whether that something survives long enough to try is the only question that matters. The Great Filter has given us the terms of the problem. The rest is up to us.